Hey everyone, welcome back to our binary search series. Let's take a look at problem number 852, peak index in a mountain array. So this problem says we have an array that is guaranteed to be a mountain and we need to return one index. So what do we mean by mountain? The array is in this shape. It increases and then it decreases at some point and we need to find the peak, the point where it starts decreasing. So in this example, we have 0, it increases to 1 and then it decreases back to 0. So at 1, it started decreasing. So we need to return that 1 and actually we need to return that index, which is 1. Similarly, in example 2, we have an array 0, it goes to 2 and then it decreases to 1 and 0. So at 2, the index is 1, so we need to return this. Similarly, we return index 1 here because at 10 it decreases. Okay, so now that we know we need to return a peak, in this example 60 will be the peak. So we have elements through 30 and the peak is 60 and then it decreases to 10 again. So I have written this way, increasing and then decreasing. And what do we return in this case? We need to return 3 because 60 is the peak. And how do we calculate the peak? If you observe carefully, any element is said to be peak if its left element and right element both are smaller than that particular element. In this case, 50 and 20, which is left element and right element to 60, both are smaller than 60. So that's when we get to know that's the peak and we return it. And none other elements apart from 60 satisfy those conditions. It can satisfy only one of those two conditions, but not both the conditions. For example, if we take 40, the element left to 40 is less than that, which is good, but element right to 40 is not less than 40, it's more than 40. So we know it's increasing here and it's not the peak. And similarly, 20, if we take the element to the right of 20 is less than 20, but the element to the left is not, it's more than 20. So that's how we know 20 is also not the peak. So there can exist only one peak in this case, and that is 60. So let's start our two-pointer approach here. We'll take the leftmost element as left and right element as right. I'm not taking low and high like our previous problems because the rightmost pointer need not be high every time because it's decreasing in this case. So let's just go with left and right. And we need to calculate the mid. So what would be the mid in this case? Mid would point to index 2, which is 50, because 0 plus 5, 0 plus 5 by 2, the floor value of this will point to 2, and that would be our midpoint to start with. So what's the first thing we do? We check if this is the peak. Is left element and right element to the mid element is less than the mid element? No, it's not. So if it is not, then we need to update either our left pointer or our right pointer to narrow down the elements. And which pointer should we update in this case? Should I move my left pointer further or right pointer behind? So if you carefully look through, the peak here is after the 50, after our midpoint, meaning at this midpoint here, we are still in this increasing direction and not found the peak. So we will find the peak somewhere here, for example. So it's more meaningful to update the left pointer from being here to somewhere here after the mid element, because we know that peak is found somewhere here. So we need to get our left pointer here. So let's do that now. We will update our left pointer to point to mid plus 1. And let's take a step back before I update our left pointer. How did we again calculate this? To update our left pointer, we need to check if this element is not peak, then is our element left to 50 or left to midpoint, is it less than 50? If yes, then we know that this is an increasing direction, and then we update our left pointer. So let's do that. Now we'll calculate the mid again. We are at left pointer 3 and right pointer 5. So 3 plus 5 by 2, which is 4. So we'll put our midpoint right here at 20. So we check the same thing. Is the left element and right element to the mid element is less than 20? No, it's not. 60 is not less than 20. So we still did not find our peak. So we need to update which pointer in this case. So to decide that, we check if the element next to mid element is less. If that's the case, we know we are in a decreasing direction and peak was somewhere here. We already found the peak somewhere here. So it will be more meaningful to update the right pointer to this one, to less than mid. So let's update our right pointer to 1 less than mid. So now the left and right both are pointing to the same element and we are here in third index. So left pointer is 3 plus right pointer is 3 and divided by 2 will give us 3. So we will put our mid at 3. And now we check, is the left element and right element compared to mid is less than mid element? Yes, it is. So we return the 60th index, which is index 3 in this case. So we found our mid. So now we discuss the algorithm. Let's write out some conditions what we discussed now. For an element to be peak, what was the condition? Its left element and right element both should be less than the mid element. Our array of mid must be greater than array of mid minus 1 and must also be greater than array of mid plus 1. So before we dive in and write the pseudocode for this, I want you to notice one interesting edge case here. So let's discuss that below with another example. Let's quickly trace this out. So we have left and right pointers here. Where do we get the mid? 0 plus 4 by 2 is equal to 2. So we get our midpoint right here. So this would be our mid. Now which pointer should I update? Left or right? I'll check if array of mid is greater than array of mid plus 1. So is 3 greater than 2? Yes, it is. So if it is greater, then I know it's in this decreasing direction. So I'll update my right pointer. So before I update my right pointer, let's write this condition quickly. How we update the right pointer? If array of mid is greater than array of mid plus 1. We update our right pointer to mid minus 1. So let's calculate the mid. 0 plus 1 by 2 will be 0, the floor value. So this will be our mid. So let's write our left pointer now. How do we calculate? If we update our left, if array of mid is greater than array of mid minus 1, then we update our left pointer. But if you take a closer look at this point, we have a bug and it doesn't work. We are checking if array of mid, which is this one, is greater than mid minus 1. If there was an element here, this would have been true. But since we don't have any element here, this will be undefined and this condition will not be successful. And the same bug holds good for this as well. Let's say if this was our mid, if array of mid is greater than array of mid plus 1. So we are comparing this, if this element is greater than mid plus 1, what if this element doesn't exist? Then this program doesn't work. So that's the edge case here, which I ran into as well. So how do we deal with this? So instead of checking array of mid greater than array of mid plus 1 when updating right pointer, what we could instead do is we can just flip this condition and say if we need to update the right pointer, if array of mid is less than array of mid minus 1. So we can flip this and write if array of mid is less than array of mid minus 1. In that case, let's say if this was midpoint, we are checking if this point is less than mid minus 1. And this mid minus 1 always exists when we are updating the right pointer because it will be in decreasing direction like this. And this element would always exist. Similarly, when we are updating left pointer, it will be in increasing order and this element, the element next to this always exists even though this element doesn't exist. So we can write when updating left pointer, we need to check if array of mid is less than array of mid plus 1. So we will be sure that mid plus 1 always exists. So that was a small edge case I wanted to show. So let's write a pseudocode now. We'll take left is equal to 0 to point to the leftmost element in the array and right is equal to array.length minus 1. So we need to run and update the midpoint and left and right pointer as long as left less than or equal to right. If right is greater than left, that means we did not find the peak and we can exit out of this while loop. So we will run this while loop as long as left less than or equal to right. And let's first find the midpoint here. Mid is equal to left plus right divided by 2 and this would be the floor value here. So I'll first check if our mid element is the peak. And how do I do that? I'll take this condition here if array of mid greater than array of mid minus 1 and array of mid is also greater than array of mid plus 1. In this case, I'll return mid, meaning we found the peak at this mid. Let's write a condition to update our left pointer like we discussed here. Array of mid less than array of mid plus 1 will update our left to point to mid plus 1 index. Else, if this doesn't hold good, then we are updating our right pointer and we'll do right is equal to mid minus 1. So we don't have to specify this condition because it anyways falls into else part then. And we will close our while loop. And the problem says we for sure will have one mid index, which is peak. So we don't have to write anything outside this while loop. So we will at some point find the mid element here and reach this return mid line. So let's run this on Leetcode. Okay, so we are back on Leetcode. I have this code written already to save some time. Let's go over this quickly. Left is equal to 0, right is equal to array.length minus 1. We will run this while loop as long as left less than or equal to right. We are taking floor value to calculate the mid, floor of left plus right by 2. And this is the condition to check if the mid element is the peak. Array of mid is greater than mid plus 1 and mid minus 1. And if array of mid is less than array of mid plus 1, notice here we are updating the left pointer and it doesn't go out of bounds because mid plus 1 always exists. We are not making use of mid minus 1 in this case. So we are covering the edge case. Else we update the right pointer to mid minus 1. Let's run this. It got accepted. Let's submit this. And it works. So that was our problem to find the peak index in mountain array. I'll give this code in the description below. If you have any questions or comments, please feel free to comment below. Thanks for watching. See you in the next video.